Welcome to This Explainer. We're diving straight into the physical laws of motion today. If you've ever stopped to wonder what exactly makes things move, stop, or completely change direction, well, this explainer is going to map the whole thing out for you. We're going to build up your understanding step by step so you can really master how these invisible forces just rule our entire world. Okay, let's dive into this. Here's our roadmap for today. We're starting with defining force. Then we'll look at the balance of forces, unpack the first and second laws, see the third law in action, analyze some complex systems, and finally, wrap up with your next steps.
Right, Section 1, Defining Force.
So at its most basic, a force is essentially just a push or a pull. But speaking scientifically, it's actually a vector quantity. And that means it absolutely requires both a magnitude, like how strong that push or pull actually is, and a specific direction. You literally can't fully describe a force without telling us which way it's acting. We measure this magnitude in newtons, written as a capital N. And remember, a force doesn't just cause things to move, it can also completely change an object's direction or even alter its shape and size.
Now, we can see these abstract concepts perfectly preserved in traditional Indian knowledge systems. Think about traditional Indian archery. When an archer pulls that bowstring backwards, the force clearly has a direction, right? But pay attention to what happens before the arrow even flies. The force applied by the archer is actually changing the shape of the bow. It's bending it. So this brilliantly proves that forces can deform an object long before they produce any actual motion whatsoever.
Moving on to Section 2. The balance of forces.
When we add up all the vector forces acting on an object, we get what's called the net force. If those forces completely cancel each other out, boom, we have balanced forces. The net force is exactly zero. But here's the critical bit you really need to understand. Zero net force doesn't just mean an object is sitting still. It can also mean the object is moving with a constant velocity, just a steady speed in a perfectly straight line. On the flip side, unbalanced forces yield a non-zero net force, and that right there is what actually produces acceleration, causing an object to speed up, slow down, or turn.
To really conceptualize this, let's picture a classic community tradition, a tug-of-war. If both teams are pulling on that rope with the exact same strength but in opposite directions, the forces are totally balanced. The net force is zero and the rope, it goes absolutely nowhere. But the very second one team manages just a slightly stronger pull, those forces become unbalanced. You've suddenly got a non-zero net force pointing towards that stronger team, and the rope, along with the losing team of course, experiences acceleration right in that direction.
Okay, Section 3. The first and second laws. Let's kick things off with Newton's first law, the law of inertia. Inertia is just the tendency of any object to resist a change in its state of motion. Basically, if it's resting, it really wants to stay resting. If it's moving, it wants to keep moving. But how do we actually measure this sort of physical stubbornness? Well, mass is the direct measure of this inertia. So the more mass an object has, imagine a massive temple chariot, for example, the greater its inertia and the harder it's going to be to start or stop its motion. Building on that, we've got Newton's second law, which gives us the actual maths behind it. First, we define momentum. We use a lowercase p for this, and it's simply the product of an object's mass and its velocity. Now, Newton's second law states that the net force applied to an object equals the rate of change of that momentum. But honestly, for most everyday objects where the mass stays constant, this boils down to that famous equation F equals ma. Force equals mass times acceleration. And crucially, that acceleration always, and I mean always, happens in the exact direction of the net force.
Which brings us to Section 4, the third law in action.
We've all heard it. For every action, there's an equal and opposite reaction. But here's the question I hear all the time. If they're equal and opposite, why on earth don't they just cancel each other out? Well, the absolutely crucial point here is that they act on different objects. Since the action force acts on object A and the reaction force acts on object B, you can't just add them together and cancel them out when you're trying to analyze just one of those objects.
To really see this in action, just look at the brilliant mechanics of a Kerala snake boat gliding through the backwaters. When the rowers pull their oars, they're applying an action force, physically pushing the water backwards. But simultaneously, thanks to the third law, the water exerts an equal and opposite reaction force, pushing the oars, and the boat attached to them, forwards. The action force is on the water, the reaction force is on the boat. Two entirely different objects. And that right there is exactly why the boat accelerates forward instead of just sitting completely stationary.
All right, Section 5, Analyzing Systems.
So here is a highly effective three-step method for systems analysis. Step 1. You draw a sort of imaginary boundary around all the connected objects you want to treat as a single system. Step 2. Any forces being exchanged between the objects inside that boundary, those are now considered internal forces. And because of Newton's third law, these internal forces occur in equal and opposite pairs, which means they actually do cancel out for the system as a whole. Finally, step 3. You only calculate the net external forces pushing or pulling from the outside, and that is what determines the entire system's acceleration.
And this beautifully illustrates the concept using some familiar Indian farm equipment. Imagine a tractor pulling a heavy harrow and a loaded trolley. Honestly, if you tried to calculate the physics for each piece individually, it'd be an absolute nightmare of tension forces in all the connecting hitches. But if you draw your boundary around the tractor, the harrow, and the trolley together, treating the whole shebang as one single massive system, all those complicated pulling forces between them just become internal. They just cancel each other out. You're left with only the external force of the engine driving forward against the friction of the ground, which makes calculating the overall acceleration remarkably simple.
Finally, Section 6. Next steps.
We know from Newton's third law that the action and reaction forces are always exactly equal. But think about this. If a lightweight object interacts with a really massive object, those perfectly identical forces are going to produce wildly different accelerations. That's F equals ma in action. The physical laws are clear, but the real test is applying them. So I have to ask, are you ready to actually calculate these variables yourself when the scenarios get a bit tough?
This is where you transition from just being a passive listener to becoming an active problem solver. Head straight over to ednudge.in to test these exact physical laws. They've got CBSC-aligned question banks and this really unique 5-step nudge system, which guides you through HOTS competency-based scenarios without just, handing you the answer. But before you go, ask yourself this one thing. If every single movement in the entire universe, from an apple falling from a tree to a rocket soaring into space, is governed by these exact same invisible forces, what else can you control once you truly master them? Head to ednudge.in and find out.